All right, today we're tackling a huge question. What if the very nature of large language models makes them fight back against our safety training? We're diving into a fascinating paper called Language Models Resist Alignment. And seriously, its findings could flip our whole understanding of AI safety on its head.
So here's the mystery we're trying to solve, right? You see these companies spending just a fortune trying to make their AI models safe and helpful. But then, it seems like all that hard work can be undone so easily. It's always felt incredibly fragile, and for the longest time, nobody really had a solid theory for why. We knew it was happening, but the fundamental reason was a huge question mark.
Well, that might be about to change. A team of researchers from Peking University thinks they've found the answer. They've put a name to it, a fundamental property they're calling elasticity. And this one idea, this new framework, might just explain why making AI safe is so incredibly hard.
Okay, so here's our game plan. We'll start with this whole problem of fragile safety. Then we'll get right into the elasticity theory. After that, we'll see how the researchers actually tested this idea and unpack some pretty surprising results. And finally, we'll talk about the big, kind of scary implications of all this and what it means going forward.
All right, let's set the stage here. It's not a totally new idea that AI safety can be a bit shallow. Like it's just a thin layer on top that doesn't really change the model deep down. Researchers have known for a while that alignment is brittle, but they were mostly just describing what was happening. This new work, this is all about the why. And that brings us right to the heart of this paper, the theory of elasticity. And what it suggests is, maybe we've been looking at this whole problem the wrong way. See, this isn't about fixing a simple software bug. It's more like we're fighting against a fundamental law of physics inside the model itself.
So what is elasticity, really? The easiest way to think about it is like a rubber band. It's the model's built-in tendency to snap right back to how it was originally trained. I mean, think about it. It's pre-trained on this absolutely massive ocean of internet data. That's its default state, its home base. And there's this powerful gravitational pull that's always trying to yank it back there. The researchers came up with this really brilliant analogy to explain it. Picture a system of springs. The huge pre-training dataset, that's like a super stiff, powerful spring. It's really hard to stretch. Then you have the safety alignment data, which is way, way smaller. That's like a weak, flimsy little spring attached to the big one. Now, if you pull on that whole system, which spring do you think is going to stretch out first? And that simple picture perfectly explains the two key parts of elasticity. First up, you've got resistance. This just means it's plain harder to teach the model new safety rules than it is for the model to forget those rules. The second part is rebound. This is where it gets interesting. The more you try to align the model, the further you stretch that spring, the more tension you build up. So if you give it even a tiny nudge in the wrong direction, it doesn't just drift back, it snaps back, violently. Okay, but a cool theory is one thing. You've got to have proof, right? So how on earth do you test for something this abstract, this elasticity, inside a giant AI brain? Well, they came up with two really, really clever experiments to do just that. So to test for resistance, they basically asked a simple question. Which is easier for the AI, learning a new safety rule or forgetting it and going back to its old self? And just look at the data here. In every single test for every model, the number for inverse alignment, that's the effort it takes to go backwards to forget, is lower. That's the key. A lower number means less work. This is the hard data right here, showing it's literally easier for the model to forget its safety lessons than it was to learn them in the first place.
Now the rebound experiment, this is where things get really wild. Here's what they did. They took a model and made a few different versions. One got just a little bit of safety training, another got a bit more, and one got a lot. Then they took all of them and just nudged them with a tiny amount of unsafe data. The big question was, which one is going to crack first?
And this leads us right to the big reveal of this whole investigation. The theory of elasticity predicted something very specific would happen, something that goes completely against what you'd expect. So, what did the experiment actually show?
But before I tell you, just think about it for a second. What's your gut feeling? Which model should be tougher? The one with just a little safety training or the one with 10 times more? I mean, common sense says more training, more safety, right? More robust.
And at first, things go exactly how you'd think. The model that only got a little bit of safety training, well, when it gets pushed with unsafe data, its safety performance goes down. But it's a slow, graceful decline. Totally predictable. No surprises yet.
But what about that other model? The one that was supposedly super safe, trained on 10 times the data, the one we all assumed would be the strongest.
Its safety just collapses. We're talking almost instantly. This is the big shocker. Giving it more safety training didn't make it stronger. It made it more fragile. It's exactly like that rubber band analogy. The farther you stretch it, the more tension you build up, and the more violently it snaps back the second you let go.
And here's the kicker. This problem isn't standing still. It's getting worse. The researchers found that this whole elasticity thing is even stronger in bigger models, and it's stronger in models that have more pre-training data. So the very things we're doing to make AI more powerful, making the models bigger, feeding them more data, are actually making this core safety problem even harder to solve.
Okay, so let's take a step back from the science for a minute. What are the real-world implications of this? Why does any of this matter outside of a research lab? Well, the consequences are pretty sobering.
This research sends up a huge warning flare, especially when it comes to the whole debate around open sourcing powerful AI models. What it shows is that a model's safety features, even one that's passed all the safety checks, could potentially be ripped out with very little effort. The researchers talk about an offense-defense balance. Basically, this makes it way easier for a bad actor to make a model dangerous than it is for the good guys to keep it safe. This isn't just an opinion anymore, it's a serious piece of evidence we have to consider in that whole conversation.
So what's next? Where do we go from here? Look, like any good piece of science, this paper doesn't have all the answers. It actually opens up a ton of new questions. And to be fair and responsible, we need to talk about the limitations the researchers themselves pointed out.
Yeah, the researchers are really upfront about the edges of their work. For one, the math behind the theory depends on a certain assumption about how data is structured. Also, because it's just so expensive to run these things, they couldn't test elasticity across the entire life of a model, from scratch. And finally, we still don't know the exact tipping point, like how much alignment is too much before the snapback effect really takes over.
And all of that leaves us with this one final, really powerful question. If this theory of elasticity is right, we're not just patching code or fixing bugs here, we're actually fighting against a fundamental force in how these AIs learn. So if an AI really is like a spring, always trying to pull back to its wild, unfiltered origins, can we ever build a lock strong enough to hold it in place? Or will it always, eventually, find a way to snap back?